All right, so today we are going to talk about low latency data processing in the era of serverless. Here is a brief agenda that we are going to cover. First, we will try to understand better what is serverless, why industry goes serverless at all. And then we will go deeper into a specific topic, how to solve low latency data processing tasks using serverless, what can be issues there, how to deal with them. And at the end, we will see how to use those approaches in a live demo. We will run a practical solution to a serverless fraud detection problem using serverless architecture. Right? A couple of words about me. In the industry, I work for more than 9 years. Before that, I worked on different positions, from Java engineer to team lead and solution architect. At the moment, also, I often speak at conferences and a member of program committee at Devox Ukraine, one of the biggest Java conferences in Ukraine. And working now as a cloud developer at Hazelcast, where my team and I are actively working to help our industry to move to the cloud. So serverless. First, this term was introduced in 2014 with the release of Amazon Lambda servers. And very often, it is associated with Lambda Functions and basically Amazon Lambdas. But is it just Lambda Functions? Let's try to figure out this. So how it historically developed and how did we get to this point where when everyone is talking about serverless. So all that started in mid-1940s, long time ago, with the first supercomputers like ENIAC that were used by militaries to do some artillery calculations. Then it evolved to 1960s to first mainframes created by IBM. Then there is a really nice quote which belongs to Fernando Corbato, very famous computer scientist that was working on Multics operating system. So in his white paper about Multics operating system, they actually predicted that computer facilities in the future will be operating like a power plant, power company, or like a water company. So that means nowadays, you don't have to build your own water facilities, your own power plant. Similarly, you will use some provider for computer resources, right? Then, over decades, we went through client-server computing model, through web enterprise computing model, and we get to 2004 when AWS released their first service. It was SQS, by the way, and it actually started era of clouds, of major cloud provider. In 10 years, cloud providers were actively developing, and nowadays, if you take AWS, it has more than 120 products, services, right? And it came to the point, as I mentioned, in 2014, they released Amazon Lambda. And it started actually epoch of serverless. And just this year, there was interesting white paper published by University of Berkeley, where they reviewed current state of serverless and did the predictions about its future. And their predictions say that in 10 years, it will be as actively adopted as cloud providers now, as the cloud computing now. Why this prediction is interesting? Because just 10 years ago, University of Berkeley published same white paper where they predicted same thing about cloud computing and cloud providers. So this is why their prediction make lots of sense. And here, if you look, both clouds and serverless, they are two different models of cloud computing. And I like to say about it, like serverless is the next step in cloud computing evolution. And cloud computing, as you probably know, this is a model where you get different resources like a CPU power, like a storage, application services. You get them on demand when you need. You usually get them over the internet and using pay-as-you-go model. So you pay only for what you use, right? Usually serverless is split into two categories. One category is backend as a services. And how does it look like? So if you take some typical cloud application, which handles traffic coming over API gateway, then distributes it using load balancer among microservices, at the backend, instead of deploying your own database, queue, building your own authentication service, you use managed services provided by cloud provider. You don't build and set up it by yourself. So this is, we call this backend as a services. Another kind is functions as a services. So functions as a services is when you run your code in stateful compute containers, which are ephemeral, and which are event triggered by various events from the cloud provider infrastructure. So what are those events? If we take Lambda function that actually represents function as a service, so this is a callback that you implement in your favorite programming language. And this callback handles specific event. So it can be uploaded to the object storage of the cloud provider so that you can handle the uploaded file, encode it, transfer somewhere else. It can be HTTP events from API gateway. So you, by doing this, you can create some REST API, and all the requests coming to API gateway will be transferred to your Lambda function, to your callback that you implemented. It can be queue as a source of the events, like a distributed queue. Instead of writing worker agent, which handles the queue, you just implement callback and provide it. Or it can be even a cron expression, so that event will be emitted on periodical basis and will trigger your Lambda function, which is very useful if you do some periodic tasks, jobs, extract, transform, load, things, and so on. Serverless, the major benefit is that of serverless is that it allows you to build and run your applications and systems without thinking about underlying infrastructure. But itself, serverless, the term, can be confusing. Like someone can guess other servers under the hood, right? But you need to keep in mind that servers are still there. And even from my experience, I can tell that we had a production system where backend was implemented in Lambda functions. We used one of three major cloud providers. And at some point, API gateway started returning error codes. And of course, we thought that this is something that our fault or our bug. But it turned out that Lambda functions in the cloud provider infrastructure just got stuck. Okay, so does it mean the serverless is bad? Function as a service is bad? It doesn't mean that, but it means that you need to think about plan B if it happens. Okay. Why industry goes serverless at all? Like why we are here sitting and talking about all that? So now I would like to ask you one question. So in IT projects nowadays, how do you think, what's the most expensive thing in IT projects?
environment.
Oh, right. Another.
Computing development.
What does it mean, development?
Developers.
Develop. All right, so you're right. So nowadays, the most expensive thing is the rate of developers. And I just spoke with one of my friends recently. They are making some startup. They are using one of those 3 major cloud providers. They are running some instances, virtual instances. They have set up some managed database, some load balancer, like some typical setup. And I asked, how much do you pay for it in a month? He told, like, before optimization, we were paying $800. Now we optimized a little bit. We pay a little bit more than $500 in a month. Startup, of course, they don't have much big workloads. But compare this to your salaries, and you get the answer. So the first thing is lower costs. And you get T-shirts. Yeah, you can come later and take. Yeah, so you can save some costs, spend it on something else. Of course, using serverless, you don't have to keep that big DevOps team, so maybe less people to go for a beer with. And you cannot go for a beer with a cloud provider, but like it's like that. Serverless, by its nature, it's cloud native. And that means things like discovery, like fault tolerance, high availability, you get them out of box. Plus, you get more elastic scaling, because you act with more compact units, like function instances. It's easier to provision them than to provision EC2 instance if you run in Amazon. It makes your system overall less complex, because you write less code for your infrastructure layer. Less complex means less time spent on the support of the system, on fixing bugs, etc. And the last, like a summary point of all this, it significantly reduces time to market. Why it's important? Because nowadays, time is, for sure, it's a main pressure point in IT projects. And how can you deal with it? You can either grow your team, or you can handle this in a more smart way, like make your system more complex, automate more, right? So serverless actually helps you to follow the second approach, all right? So now we just went over the serverless itself and saw how we get to this point historically. And now, but what if we want to solve some very specific problem, for example, low latency data processing? Can we do this in serverless? Is there any chance? First, let's go over typical scenarios of low latency data processing. So first thing which comes to mind is algorithmic trading in financial markets. So when you have to quickly evaluate situation state of the market and decide whether to buy or not certain stock option. And you have to do this in rate of milliseconds. Another good example is real-time bidding for ads. So every time you open a page with a Google Ads, under the hood, Google opens auction. Advertiser bid for this auction, and Google chooses the best matching ad in terms of money, in terms of matching to the concrete person. It's also done very quickly in the rates of milliseconds. Fraud detection for the in-flight transactions. Every time you pay for something, the underlying bank is checking whether there are signs of fraud in this transaction that you perform. Another example, personalized user experience in e-commerce. Let it be e-commerce or something else. Currently, every application tries to analyze your every step. So everything that you do gets collected into some click stream, and it is analyzed to predict your next actions to decide which product or ad to show you. What can bring latency in serverless when you're using Lambda functions? So let's see a typical life cycle of the Lambda function. So all starts with the very first request, which comes to a Lambda function, to the callback that you implemented. And it triggers call start. So the good example in real life is when you wake up, you are still sleeping a little bit, and somebody calls you and trying to explain some problem. Like you cannot get what's going on. Yeah? So it needs some time for you to initialize your runtime, to provision your memory, right? To restore it from the disk, and so on. So all that is very expensive, and this is called call start in Lambda functions. Then every request that Lambda function handles goes over state transition. So Lambda function, when handles every request, it goes over state transitions. Those states are freezing. So after every request is handled, it freezes its state. All the threads are descheduled from CPU, are put on pause. Similar happens to background processes. And before every next request, function thaws. So threads are starting scheduled on the CPU. Background processes are resumed, and so on. And at every moment, your function instance can be terminated. So it can be done either based on some timeout. For example, most of the cloud providers terminate Lambda function if it is not receiving requests for more than 5-10 minutes. Or it can happen due to a load spike on the cloud provider infrastructure. Because keep in mind that you are still running in shared infrastructure, and there can be increased load on another account, which is also using Lambda functions. So in order to allocate resources, if you don't get a load at this moment, your functions will be terminated and released. Yeah, and as you can see, there are certain points which can bring latency in our case. So for sure, it's a call start, which brings most of the latency and slowness. It's this Lambda function state transition, because we cannot afford ourselves anymore to do some health checking, to check for topologies changes in the database cluster that we connect to, or change for API liveness. We call some API. We cannot rely on it. And at every moment, our function can be terminated, and every state that we pre-cached internally in memory, it's gone. So how to optimize this? How to deal with those issues? Popular approach is making periodic requests to the function to keep it warm. So how does it work? So usually we use either cloud provider service or spin up some agent which makes periodic requests without no business payload that are just signaling cloud provider to prevent function termination. Okay, so by doing this, we prevent this cold start latency. Another example is CPU-bound tasks. So we are talking here about encryption, about some image encoding. So those tasks are they depend on CPU resources. And you need to know that a Lambda function CPU resources, they are proportional to the memory resources that you allocate. So for example, in case of, again, Amazon Lambda, because I worked more with that cloud provider, if you provision 1 and 8 gigabyte of memory, you get multi-core Lambda function. And it helps you to save your costs, because in case of Lambda function, the less processing time is, the less you pay. So with more CPU resources, in some specific cases, your Lambda function will finish sooner, and you will pay less. Right? So you need to allocate more memory in those cases. Another very important point is how do you deploy your application. So again, if we take some cloud application, it may use different managed services for database, for user authentication, for object storage. And it's not always the case that they are located in the same region, in the same availability zone. So when you design your system, you need to make sure that they are, we can place them as close as possible one to another. So they should be allocated in the same region, in the same availability zone, in the same virtual private cloud, VPC. And another thing that I can also tell about Amazon is that if you place them in the VPC, it sounds strange, but you can get more latency because it will take some efforts to initialize a network stack to VPC. A third approach is to cache a Lambda function state, because again, you may have some hot data, which is read-mostly data, rarely updated. And as Rafal just explained, so caching usually the first thing that you should think about when you deal with some performance issues. So how we usually do this? We use some external low latency in-memory storage. And instead of storing state, some data inside of the Lambda function, inside of the fields of your class object, you store them separately in external in-memory storage. So why people usually choose in-memory store for those tasks? Here is a really nice spreadsheet. Latency numbers every programmer should know. So they are updated every year, so I really encourage you to read it. And if you look there, so you can see that 1 megabyte sequential read from the disk is around 1 millisecond. One sequential read from SSD is 78 microseconds. And 1 megabyte read directly from memory is about 5 microseconds. So those numbers talk for themselves. This is why, in case if you need to cache something, you go for in-memory storages. And in 2019, I can say we can call microsecond a new millisecond, because more and more often people operate with microseconds. All right, so this is why we choose in-memory computing. So now we went over different approaches to optimize serverless computing, Lambda function processing. Now let's see how to apply them in a practical task. So here we will be solving a simplified fraud detection problem. So we're going to have a bank of Hazelcast, which processes transactions made in airports. And we will be analyzing, we will be getting transaction. And bank of Hazelcast backend will be checking coordinates of the airports, time of the transactions, and will be deciding whether it was realistic for user, for the client, to move from one airport to another. So here in this case, first transaction was performed in London, second in Paris, and we can see there are 2 hours between them. So we can conclude this transaction looks fine. But if that would be Sydney and just 2 hours between transactions, we would analyze coordinates of the airports, and we would conclude that this transaction looks suspicious. So we're going to have 2 Lambda functions. First Lambda function will be subscribed to S3, will be handling uploads. So we will be uploading a read-mostly static data set with airports data. We will be having like an airport code, name, and coordinates. And our Lambda function will handle upload and will copy this data to Hazelcast cluster that we spin up in Hazelcast Cloud. And we will see how we do this. Another Lambda function will be subscribed to API gateway, will be receiving the actual payment transactions, and it will use airports data that we imported to Hazelcast cluster, will be saving user history, will be using this user transaction history to calculate the actual fraud detection. And also, we will have a CloudWatch events. CloudWatch events is one of the features of AWS CloudWatch service that allows you to emit periodical events. And you can specify that this event should trigger a Lambda function. So we will be sending keep alive events to our Lambda function. Okay. So why we are using Hazelcast here? So what is Hazelcast Cloud? You already heard something about this. So yeah, as Rafal said, it's a managed service for Hazelcast in-memory data grid. Just to sum up, when I usually quickly explain what is in-memory data grid, you can think of it as of distributed cache, which stores all data in memory, which is clustered. Usually it is peer-to-peer clustering, and which allows you to do different computations and calculations on the data that you store. So this is in-memory data grid. Why Hazelcast Cloud can be useful if you run using some cloud provider? Because it allows you to create a cluster in the same region, availability zone, where your infrastructure runs, and that allows you to achieve a lowest possible latency. It comes with a full feature-packed security, so you get encryption of the data in transit. And it is Lambda ready, as we will just see very soon. Okay, and now let's see our demo. So first, let me show what I prepared at AWS. And later, we will see the code. So here, I have 2 Lambda functions. This is, let me increase, validate function and S3 function. So if I go to S3 function, we can see that it is subscribed to S3 bucket and Cherkas Cloud demo. And if we open validate function, it is subscribed to API gateway, as I said, plus it is subscribed to CloudWatch events to receive those keep alive messages. All right, and another thing I would like to show you is the way we configure our Lambda function. So here you see on UI we specify some properties. Under the hood, those properties are accessible through environment variables, and we can configure them, update them using AWS CLI. And those properties actually are the cluster name, password, and discovery token that Rafal just used in his examples. So we will be also using this discovery mechanism. OK. Here we got API gateway, which is integrated. So we have a validate endpoint, which is integrated with a Lambda function that we just saw, cloud demo validate function. And we also have our CloudWatch rule, which sends a keep alive message every 5 minutes to our Lambda function. OK. Now, I'm going to, since I don't have a cluster ready yet, I'm going to create it and show you how I do this. So here what you see is a web console of Hazelcast Cloud, a control pane. And yeah, so I need to give a name to my cluster. I choose cloud provider, region. Then I can select one of the 4 cluster types. There is a free cluster type, which allows you to store up to 2 megabytes of data. And you will get only 1 cluster member. So you remember Rafal was showing 2 cluster members. So here there will be 1 cluster member, but for free. And you get small, medium, and large clusters. So with a maximum data set that you can store up to 375 gigabytes. Okay, and another options that are available are auto-scaling. So our cluster can grow as we write data into it, or we can statically set a memory that is available to us. Then we can enable persistence. That means cluster data will not be lost between cluster restarts. We will be, under the hood, we will be storing it into persistent storage. And you can choose data in transit and to specify some IP whitelisting. So that cluster will be accessible only from a certain IP range or IP mask. And the last one is map configuration. So you can configure Hazelcast data structures. Hazelcast provides various data structures like a map, queue, list, distributed set, and many more. And here you can specify map configuration. So here I'm going to configure user's map. And I'm going to specify a time to live. I will set user's map. We are going to use user's map for historical data. So we will set 12 hours as the time to live. So that the entries which are older than 12 hours will be automatically removed. Okay, so I add this config. And I trigger cluster creation. So under the hood, just to say a couple of words of it, we actively using Kubernetes. So just at this moment, our infrastructure provisions new Hazelcast cluster using Kubernetes facilities that we have in AWS. Meanwhile, let me show the code. So here I have a project built using Spring Cloud function. And we've got 2 Lambda functions. So one Lambda function is a S3 function, which simply receives a S3 event. What we do is we just read this event. It comes in JSON format. We deserialize it. And we write it into our airports map. So another map that we are going to use is airports map. And every airport comes with a airport code, description, latitude, and longitude that define coordinates. Okay. Another Lambda function is validate function. So this Lambda function implements the actual fraud detection logic. Here you see we get 2 maps. They are injected using Spring Cloud function dependency injection. And here you see the switch case, meaning that we will be handling 2 types of events. One is validate event, and another is keep alive event. For the keep alive, we just do nothing. And we run our logic. So what does our logic here? We first check if we have historical data for this user. If not, we just save it for the future validations. Otherwise, if we have historical data, we retrieve airport that we got from request and the last used airport. And having 2 transaction timestamps, we can calculate time between 2 transactions and distance between 2 transactions. Here we use harvesting formula to calculate distance. And then we having meters and distance and time, we calculate speed and compare it to some regular plane speed. And we decide whether this realistic speed or not, and whether this transaction looks suspicious or it looks fine, right? And we return result back to API gateway, which forwards this back to a caller. Okay. So another thing I would like to show you is our function application that we defined using Spring Cloud function framework. So here you see we have several bins. One bin is a Hazelcast client bin. So here we pass those properties that I mentioned, discovery token, right, and some other properties. Then from this Hazelcast client instance, we retrieve two maps. So we retrieve users map and airports map so that we can work with them later. And we define another bin, Amazon S3, that we use to copy data from S3 to Hazelcast cluster. Okay, does it make sense so far? How it will work? Okay, so let's go back to our console. You see that cluster is up and running. So what I'm going to do now is, so as you could see, there are some properties that I used previously. They were specified for the cluster that I deleted. So I need to update them. How do I do this? Is I go to Hazelcast Cloud console. Here we have a configure client dialog, which allows you to download ready code samples, which already out of box work with this cluster on Java, Node.js, Python, .NET, and Go. Or I can do this by myself, implement client setup. So for this, I can access directly cluster password and discovery token. So I copy them. And then I go to command line. Let me increase it. So here I prepared the script which updates Lambda function configuration. So I need to export environment variables.
Could you zoom in, please?
Hmm?
Zoom in.
Yeah.
What about white background?
To be honest, I don't remember how to change it. Can you see it now? You get a nice green color. Come on. Yeah, so let me export this. Okay, let me just have something wrong with export. Okay, let me just copy it from my previous demo. Yeah, here we go. So here I specify those properties. So I specify password, and I specify discovery token. Yeah, just wrong. Here should be password. Yeah, like this. Yeah, so I set those environment variables. This is cluster name, discovery token, and password. And then I run my script. Yeah, so script updates Lambda function configuration. It will now work with my newly created cluster. And at the end, it is calling API gateway to verify if everything works fine. Yeah, we get a message, OK. This is a message that we return on keep alive request. And now, what I should going to do next is I go to S3, and I need to upload my static data set about airports. So here is my bucket, and airports JSON. Upload. OK. And now I go to CloudWatch logs, and will show you how my Lambda function handles those events. OK, so they come with some latency. Need to wait a little bit. Yeah, here we get the logs. Again, this is not real-time logs. Yeah, so here our client gets built and connects to the cluster. Yeah, as you can see, since I created a cluster with 2 members, it connected to the cluster. It handled a file with airports data and copied it to cluster. If I go to cluster now, I can see that I've got metrics for 2 maps. There was no those graphs before that. And you can see that for the airports data, our entry count graph is growing because we imported data. Okay. Now what we have is we get our airports data in Hazelcast cluster, and we have our validate Lambda function waiting for the transactions to validate. All right, so now I need to go to command line again. Yeah, and let's try to play with it. So yeah, so here I have some prepared command. And what we pass here, we pass type of the request, validate, not keep alive. We pass user ID, let's put 1. And then I pass, let me pass a live airport. So usually every quarter at Hazelcast we have engineering meetups. So all teams come to Istanbul to meet with each other. And usually I fly there from Lviv airport. It's around, the flight that I use is around 6 p.m. На тачбарі? Дякую за пораду. Ну, я думаю, що всім видно. Yeah, so it's around 6 p.m., as I said. And let's imagine that I buy some coffee at airport around this time, at 6:30, for example. So let's see what we get as a response to this request. So we see that user data is set for future validations because we didn't have historical data before for this user. Okay, now imagine that I come to Sabiha Airport in Istanbul. This is airport on Asian side. And I usually choose this airport because our office is also on Asian side. So I specify airport code, SAW. And I specify transaction timestamp, which is 2 hours later, because it takes around 2 hours to come from Lviv to Istanbul. Right, so let's see what we get here. You see that transaction is OK because it calculated using harvesting formula distance. It evaluated speed and decided that transaction is fine. But imagine that just in 15 minutes, bank receives another transaction performed in Sydney, which has airport code NSW. Right, and we here put like 15 minutes later. What we get in this case? Yeah, you see the transaction is suspicious because, at least so far, there is much work to do for Elon Musk. We still cannot move from Istanbul to Sydney in 15 minutes. All right, so that's it about my demo. And now let me switch back to the slides. So let's do some summary. So as you could see from this presentation, serverless is a perfect match when you need to move fast, because you can see that with not that much code, we get a distributed solution using managed cache service, using object store that was doing some business logic. You can do low latency processing, but you should be aware about the things that can bring slowness to your processing when you use Lambda functions. When you choose for the storage where to store Lambda function state, you need to think about high availability and latency of that storage, for sure, because this is why we didn't choose SQL database for our solution. And using the memory computing, you can reduce your function as a service cost, because the less latency you have, the less you pay, as I already mentioned. OK, and feel free to try it out. It's publicly available. And what I can add to it, we are hiring, by the way, so you can go to Stack Overflow jobs and find our job postings. That's it from me. Ready to hear your questions.
I have one question about general cloud functions. Do we have different deployment strategies for Lambda functions? Is it possible to make canary release blue-green?
Actually, under the hood, it doesn't allow you to choose some strategy. So under the hood, as I know, it just updates all of them. So if you make some mistake and your functions are failing, then you can do green-blue deployment on your own, and you can work around this. But at least for now, they don't allow you to choose some specific deployment strategy.
And second question, what about networking time with this in-memory database? Does it really matter about time in milliseconds or how do you say?
Microseconds?
Microseconds, if the networking is still 5 milliseconds or 10 milliseconds.
The thing is that nowadays, networking, I can say, is not longer bottleneck. Because if you really need to do some high-performant processing, there is lots of available software, lots of available hardware that can help you to achieve less than microsecond latency. So network is not bottleneck anymore. If we take this cheat sheet that we reviewed, so that was just the latency of 1 megabyte read, but you should also add to it SSL encryption, still network round robin. So, but it still matters.
It really depends on how many transactions you need to.
Yeah, of course. So the less latency is, the higher throughput you can achieve.
So it is usually if it is one transaction, it doesn't really matter, but if it is 1,000 transactions.
Nazarii, I have a question. How about some configuration of partitions and applications?
Sure. So actually, we have two versions. One is public cloud, and another is dedicated cloud. For dedicated cloud, it has more settings available, and this allows you to set up a more isolated infrastructure. But for the public cloud, we are going to add more and more. So there will be, I think, possible in the future to specify a partition count or something like this.
And is there any API to start the cluster? Because, for example, we have a Terraform that picks up all our infrastructure. Is there any way?
Did you change your job recently? You're at DevOps now? I'm just kidding. So actually, it's also on the way. So we're also working on some public CLI and so on. We still have some APIs, but they are not public. So if you decide to use them, we don't guarantee compatibility, like that it will be not compatibility broken. Yeah. Okay, guys, then thank you for your attention.
One more question.
Okay.
Okay. From your experience, why is not the best case to use serverless approach?
When it is not best case to use serverless approach, I can bring you one example. So there was recently an interesting blog post where a guy was paying like $300 for his production, and he was running it on EC2 instances. And actually, his traffic had the nature that he was handling over the day many requests, like 10 million requests or something like this. And in this particular case, he decided to move to Amazon Lambdas. And of course, because overall during the day, he was getting lots of requests, but he wasn't getting a really much throughput at the second or at the minute. Written everything in Lambda function, and he said that, okay, like now I have a 2 times bigger bill because Lambda functions bill you for the processing time and for number of requests that you handle. So in this particular case, there is no much sense to use Lambda functions because at this scale, they won't give you much benefit. They won't save you the costs. So this is one of the examples. So and after posting this blog post, lots of people explained to him that this is a wrong use case for the Lambda function, because your load is not that big, and you compare like $300 with $600. Like it's at that lowest cost, it's not comparable. So one of the cases when it's not a good fit.
I can also add, it's bad when you have a lot of traffic per cloud function call. If you have some few megabytes of traffic running through your function, it will cost much more because of traffic.
It actually, yeah, because you will be getting, so it depends if you get traffic from the internet, like coming outside, it will charge you for the traffic. But if it's Lambda inside VPC and it's internal traffic, it won't charge.
No, it will if we talk about Google Cloud.
In Google Cloud can be different. I mostly worked with Amazon. Okay.
Thank you for a nice presentation. And my question is, have you used some tools for provision infrastructure resources around your Lambda function?
So I can say that in my projects where I used Lambda functions, that was done by Terraform. And that's basically everything you need, because you don't need Ansible anymore to provision the container or instance. So it's done simply by Terraform. And by the way, at Cloud API, so it is possible now to provision everything using really nice, fancy JavaScript API. And it's looks better than YAML and that stuff. Okay, thank you again.